Welcome to this gentle exploration of one of the universe's most beautifully terrifying secrets. Tonight, we drift into a contemplation that seems to defy logic itself. The possibility that nothingness, the very emptiness between atoms, between stars, between thoughts, might hold within its silent depths the power to erase everything we know and love in a single, imperceptible instant. There is something almost musical about this paradox, isn't there? The idea that the most abundant thing in our universe, empty space itself, might be our most dangerous companion. Picture, if you will, the vast stretches of apparent nothingness that separate the galaxies, those cathedral-like voids that seem so peaceful, so benign, yet within these quiet chambers of existence, quantum fields whisper secrets that could make even the most hardened physicist pause in wonder and, perhaps, just a touch of cosmic vertigo. The ancient philosophers once asked whether true nothingness could exist, and now our modern understanding reveals that their question was more profound than they could have imagined. For what we call empty space, this theater in which all cosmic dramas unfold, is neither empty nor completely stable. It writhes with invisible activity, pregnant with possibilities, both creative and destructive, like a calm ocean surface beneath which unknown currents flow. Consider for a moment the air around you as you listen to these words. Between the molecules of oxygen and nitrogen, between the atoms themselves, stretches space that appears empty to our senses. Yet quantum mechanics tells us a different story, a tale of fields fluctuating at the very foundation of reality, of particles popping into existence and vanishing again in time frames so brief they mock our understanding of what it means to exist. This is the gentle terror we explore tonight, that our universe, with all its galaxies and stars, its planets and life, its beauty and complexity, might exist in what physicists call a false vacuum, a state that appears stable, like a ball resting in a shallow depression on a hillside, unaware that just beyond lies a much deeper valley. And should that ball ever find its way over the edge, should the fabric of space itself discover a more comfortable arrangement, everything we know would be transformed in an instant, replaced by something utterly alien. But why should such an abstract concept concern us? Why should we peer into this particular abyss when there are so many other wonders to contemplate? Because within this paradox lies something profound about the nature of existence itself. The very fact that we can contemplate our own cosmic fragility, that conscious beings emerged from quantum fields to question the stability of those same fields, represents one of the universe's most beautiful achievements. There is something profoundly calming about confronting the possibility that our entire reality might be temporary, built upon foundations that are stable only for now. It reminds us that every sunset, every human connection, every moment of wonder carries with it a precious impermanence, not because vacuum decay is likely to occur. Indeed, the probabilities involved stretch far beyond the current age of the universe, but because the very possibility teaches us something essential about the delicate dance of existence. The quantum vacuum, far from being empty, seethes with activity. Fields oscillate, particles briefly materialize from nothing and return to nothing. And the very geometry of space-time itself fluctuates at scales so small they challenge our concepts of measurement. This is not the sterile void our ancestors imagined, but a vibrant foundation from which everything emerges and to which everything might one day return. As we embark on this journey together, we'll discover that the question of vacuum stability touches on nearly everything we know about physics, from the smallest subatomic particles to the largest structures in the cosmos. We'll explore how scientists came to realize that the peaceful emptiness of space might be an illusion, how the discovery of the Higgs field added new dimensions to this ancient puzzle, and why the very forces that allow atoms to exist might someday decide to rearrange themselves into something entirely different. Yet this is not a journey into despair, but into wonder. For in understanding the precarious balance upon which our universe rests, we come to appreciate the magnificent improbability of our existence, the cosmic lottery that allowed complexity to emerge from simplicity, consciousness to arise from matter, and questions to be asked about the very nature of asking questions. So settle back, let your mind drift across the vast spaces between stars, and prepare to contemplate the beautiful fragility of everything that is. Tonight, we explore not just a scientific theory, but a meditation on existence itself, a gentle reminder that we are both the universe contemplating itself and temporary patterns in the cosmic dance that could change, without warning, into something entirely new. In the quiet depths of this contemplation, we must first understand what physicists mean when they speak of nothing, for their definition would have astonished the philosophers of ancient Greece and continues to challenge our most basic intuitions about the nature of reality. What we call the vacuum of space is not the simple absence our minds naturally envision, but rather a complex tapestry of quantum activity that forms the very foundation upon which all of existence is woven. Picture, if you will, the space between your hands as you hold them apart in the darkness. Classical physics, the comfortable realm of Newton and everyday experience, would tell us that this space contains simply nothing, an absence, a void, a stage empty of actors. Yet quantum mechanics whispers a very different story, revealing that this apparent emptiness is actually bustling with activity so fundamental and so rapid that it escapes our direct perception entirely. There is something almost magical about quantum fluctuations, these ghostly appearances of particles that materialize from nothingness and vanish again in time frames so brief they seem to mock our understanding of causality itself. Imagine if you could slow time to witness this invisible ballet. Pairs of particles, electrons and positrons, photons, quarks and antiquarks, spontaneously emerging from the quantum foam like bubbles rising from the depths of an infinite ocean, existing for mere fractions of a second before annihilating each other and returning to the void from which they came. This is not science fiction or philosophical speculation, but measured reality. These virtual particles, as we call them, have effects we can detect and predict with extraordinary precision. They alter the behavior of electrons and atoms. They influence the way light propagates through space, and they contribute to forces we can measure in our laboratories. The empty space around us is actually a seething ocean of potential, a quantum sea in which the waves are possibilities themselves. Meanwhile, across the vast expanse of cosmic history, our understanding of nothingness has evolved like a slowly dawning recognition. In the early days of physics, The luminiferous ether was proposed to fill all of space, a subtle medium through which light waves could travel. When careful experiments revealed no such medium existed, physicists initially celebrated the discovery of empty space. How beautifully ironic that this empty space would later prove to be far more complex and active than the ether it replaced. The transition from a classical emptiness to quantum fullness represents one of the most profound shifts in human understanding. Where once we saw absence, we now perceive presence. Where once we imagined void, we now know there is substance. The vacuum state, the lowest energy state of quantum fields, is not empty but full, not inactive but dynamic, not simple but elegantly complex. Yet this is only the beginning of the story we must tell. For these quantum fields that permeate all of space exist in different possible states, like a vast musical instrument capable of being tuned to different pitches. The vacuum we experience, this particular arrangement of field energies that allows atoms to be stable, electrons to orbit nuclei, and complex chemistry to emerge, might be just one of many possible configurations. As we drift deeper into this mystery, we encounter the possibility that what we call the vacuum might be what physicists term a false vacuum, a state that appears stable from our limited perspective, but is actually metastable, like a ball resting in a shallow depression on a complex landscape of hills and valleys. This ball might sit comfortably in its current position for eons, but the deeper valleys beyond represent configurations of space itself that are even more energetically favorable. It is both humbling and beautiful that our entire universe, with all its complexity and wonder, might exist in what amounts to a temporary arrangement of quantum fields. Every atom in your body, every star in the sky, every thought in your mind depends on the current configuration of these invisible foundations of reality. Change the vacuum state, and the very rules that govern matter and energy would shift, potentially making our familiar world impossible. There is something profoundly calming about contemplating this quantum foam, this ceaseless activity that underlies all apparent stillness. In every cubic centimeter of empty space, virtual particles dance their brief existence. Fields fluctuate through their quantum possibilities, and the universe continually recreates itself at the most fundamental level. We are not separate observers of this process, but integral parts of it, our very atoms emerging from and returning to this same quantum substrate. Perhaps the most beautiful aspect of understanding quantum nothingness is how it connects us to the cosmos in ways both intimate and vast. The same quantum fields that allow virtual particles to flicker in and out of existence in the space around you also extend throughout the observable universe, linking every point in space through their subtle correlations and shared foundations. And in this dance of something and nothing, of presence and absence, of stability and change, we find one of the universe's most elegant teachings: that reality is not built from solid, unchanging building blocks, but from relationships, from processes, from the endless creativity of fields that know how to be both empty and full, both nothing and everything, both temporary and eternal. There is something deeply soothing about landscapes, the gentle roll of hills against the horizon, the way valleys cradle morning mist, the manner in which mountains rise and fall in patterns that speak to something ancient in our souls. Tonight, we journey into a landscape far stranger and more fundamental than any found on Earth, yet one that determines the very nature of our reality, the energy landscape of quantum fields, where the peaks and valleys are not made of stone and soil, but of pure possibility itself. Imagine, if you will, that you could visualize energy as geography. Picture a vast terrain stretching infinitely in all directions, where height represents energy levels and the contours map out every possible configuration of the quantum fields that permeate space. In this abstract landscape, our universe, with all its galaxies, stars, and the atoms that compose your very being, corresponds to a particular valley, a specific arrangement where the fields have settled into what appears to be a comfortable, stable configuration. In this energy landscape, stability reveals itself through the gentle metaphor of a marble rolling across an undulating surface. When the marble comes to rest in a valley, it has found a point of equilibrium, a place where the forces acting upon it cancel out, where it can remain indefinitely unless disturbed by some external influence. The deeper the valley, the more stable the configuration, the more energy required to dislodge the marble and send it rolling toward some other destination. Yet this is only the beginning of our exploration into the topology of existence. For in the realm of quantum fields, there can be valleys within valleys, false floors that appear solid but conceal even deeper chambers below. A marble might rest comfortably in what seems to be the lowest possible position, unaware that the true ground lies far beneath, accessible only through quantum tunneling, that mysterious process by which particles can pass through barriers that should, by all classical reasoning, be impenetrable. Meanwhile, across this infinite energy landscape, every point represents a different possible universe, a different set of physical laws, a different dance between matter and force. Some peaks correspond to configurations so energetically unfavorable that they cannot sustain complex structures. Universes where atoms would be unstable, where chemistry could not emerge, where the delicate balance necessary for stars and planets and life would be impossible to maintain. The valleys, by contrast, represent stable configurations where the laws of physics allow for complexity and structure. Yet among these valleys, there are shallow ones and deep ones, temporary resting places and permanent homes. Our universe appears to reside in one such valley, but the question that haunts modern physics is whether this valley represents the deepest possible configuration, the true ground state of reality, or merely a comfortable depression with even deeper possibilities lying hidden beneath. This uncertainty transforms our cosmic perspective in profound ways. Consider the apparent permanence of the physical constants that govern our world, the strength of the electromagnetic force, the mass of the electron, the rate at which time flows. These seem as fixed and eternal as the mountains, yet they might be nothing more than temporary features of a particular valley in the energy landscape, subject to change if the fields that create them were to discover a more favorable arrangement. There is something almost musical about the way physicists describe these transitions between different energy states. They speak of resonance and tunneling, of barriers and transitions, using language that evokes both the concert hall and the quantum realm. For indeed, the quantum fields that fill all of space can be thought of as instruments playing an cosmic symphony, currently tuned to harmonies that allow for atoms and molecules and the complex chemistry of life. As we drift deeper into this contemplation, we encounter the beautiful and terrifying possibility that our comfortable valley might not be the final destination in the energy landscape. Like travelers who have found a pleasant meadow and settled there for the night, unaware that paradise lies just beyond the next ridge. Our universe might exist in a state of false stability, a metastable configuration that could persist for cosmic eons or transform in an instant. The mathematics that describe these energy landscapes possess their own austere beauty, equations that map the relationship between field configurations and their corresponding energies. These formulas reveal that while some transitions between valleys require enormous amounts of energy, like trying to push the marble up and over a high mountain pass, others might occur through the ghostly process of quantum tunneling, where the marble simply appears on the other side of the barrier without ever crossing the peak. Perhaps the most beautiful aspect of understanding energy landscapes is how they reveal the contingent nature of everything we take for granted: the stability of atoms, the behavior of light, the flow of time itself. All of these might be temporary features of our current valley, subject to change if the universe were to discover a deeper, more stable configuration in the vast topology of possibility. Yet there is something profoundly calming about this perspective as well, for it reminds us that we are not separate from this energy landscape, but part of it, temporary patterns in the field, configurations that give rise to matter and consciousness. We are the universe, exploring its own possibilities, conscious ripples in the quantum fields, contemplating the valleys and peaks of their own existence. And in this dance between stability and change, between the permanent and the transient, we find ourselves in a story far grander than any human narrative, a cosmic tale of fields seeking their most comfortable arrangement while giving rise, along the way, to galaxies and stars and planets, and eventually to beings capable of mapping the very landscape from which they emerged. In the gentle darkness of contemplation, we must now face a possibility both beautiful and unsettling: that our entire universe, with all its apparent solidity and permanence, might exist in a state of cosmic precariousness, balanced like a sleepwalker on a narrow bridge, unaware of the vast emptiness on either side. This is the hypothesis of the false vacuum, a theory that suggests everything we know and love might be built upon foundations that are stable only temporarily, subject to a transformation so complete it would redefine the very meaning of existence. Picture, if you will, a sphere balanced perfectly on the rim of a bowl, motionless and seemingly secure. To casual observation, this sphere appears to have found its proper place, a position of equilibrium where it can rest indefinitely. Yet any physicist would recognize immediately that this is false stability, a configuration that could persist for hours or years, but one that must eventually yield to the deeper truth of gravity. The sphere will inevitably roll down into the bowl's interiors, finding there the true stability that was always waiting, always available, always more favorable than its precarious perch on the edge. Our universe might find itself in an analogous position in the vast energy landscape we explored earlier. The quantum fields that permeate all of space, that give mass to particles, and determine the strength of forces might currently exist in what physicists call a false vacuum, a valley that appears deep and stable from our limited perspective but is actually shallow compared to much deeper possibilities that lie hidden in the complex topology of quantum reality. This possibility emerged from the fertile ground of theoretical physics in the 1970s when scientists began to understand that the vacuum of space was far more complex and dynamic than previously imagined. They realized that what we experience as empty space is actually filled with quantum fields in their lowest energy states, but that lowest might not mean absolutely lowest, merely the deepest valley that the fields have discovered so far in their cosmic journey. There is something almost dreamlike about imagining our universe's journey through this energy landscape. For billions of years, the quantum fields have remained in their current configuration, allowing atoms to form and stars to shine, galaxies to dance their slow gravitational ballet, and on at least one small planet, life to emerge and consciousness to flower. All of this vast epic of cosmic evolution might be nothing more than an extended pause in the field's search for their true ground state. Meanwhile, across the infinite expanse of possibility, the true vacuum state awaits, a configuration of quantum fields that would be more energetically favorable than our current arrangement, but also potentially incompatible with everything we recognize as reality. In this deeper valley, the laws of physics themselves might be different. The particles we know might be unstable, and the delicate balances that allow for complex chemistry might collapse into something utterly alien. The transition from false vacuum to true vacuum would not be a gradual process of decay and dissolution, but an instantaneous transformation propagating outward at the speed of light. Imagine a bubble of new reality expanding through space, carrying within it a completely different set of physical laws. At the boundary of this bubble, our familiar universe would simply cease to exist, replaced by something as different from our current reality as our reality is from pure emptiness. Yet, this is only the beginning of our contemplation of cosmic precariousness, for the beautiful and terrifying truth is that we cannot know with certainty whether we exist in a false vacuum or a true one. Our measurements can tell us about the energy of our current configuration, but they cannot reveal whether deeper valleys exist beyond our observational reach. We are like inhabitants of a valley who have never seen the mountains that surround them, unaware of what other landscapes might lie beyond. As we drift deeper into this mystery, we encounter the profound question of probability and time. Even if our universe does exist in a false vacuum, the transition to true vacuum might be extraordinarily unlikely, so improbable that it might not occur for time periods that dwarf the current age of the universe by factors of trillions upon trillions. The universe might remain in its current state far longer than stars will shine, longer than protons will decay, longer than any process we can currently imagine. There is something profoundly human about our response to this cosmic uncertainty. We who live our brief lives on a small planet, whose individual existence spans mere decades in a universe billions of years old, find ourselves contemplating the stability of reality itself over timescales that stretch our imagination beyond its limits. It is both humbling and oddly comforting to realize that even the universe itself might exist in a state of temporary stability, subject to changes that would transform everything we understand about existence. Perhaps the most beautiful aspect of the false vacuum hypothesis is how it connects us to the fundamental creativity of the universe. We are not merely passengers in a static cosmos, but participants in an ongoing exploration of possibility. The same quantum uncertainty that might someday transform our vacuum state is the source of all the complexity and beauty we observe around us, the unpredictability that allowed galaxies to form from smooth early conditions, that sparked the chemical evolution leading to life, that makes consciousness possible. And in this dance between stability and transformation, between the known and the unknowable, we find ourselves in exactly the right place for wonder, neither completely secure nor immediately threatened. We exist in a space where we can contemplate the deepest questions about reality while still marveling at the sunset, still forming connections with other conscious beings, still participating in the universe's ongoing attempt to understand itself. In the end, the hypothesis of false vacuum does not diminish our existence, but enriches it, reminding us that we are part of a cosmos far stranger and more magnificent than we ever dared imagine, a universe where even nothingness is creative, where stability itself might be an illusion, and where conscious beings have emerged to contemplate the very foundations of everything that is. In the quiet corridors of theoretical physics, during the transformative decade of the 1970s, two brilliant minds were about to unleash an idea so profound and unsettling that it would forever change our understanding of cosmic stability. Sidney Coleman, a physicist known for his elegant lectures and deep insights into quantum field theory, and Frank DeLucia, his gifted student, were exploring the mathematical landscapes of quantum mechanics when they stumbled upon a possibility that would make even the most hardened scientists pause in contemplation. There is something almost poetic about the way revolutionary ideas emerge in physics, not with dramatic fanfare or sudden revelation, but through the patient following of mathematical threads, the gentle pursuit of logical consequences, the willingness to ask questions that others might prefer to leave unexamined. Coleman and DeLucia were investigating the behavior of scalar fields, those fundamental quantum fields that permeate all of space. When they began to realize that these fields might not always remain in their current, apparently stable configurations. Picture, if you will, the intellectual atmosphere of the early 1970s. Physics was experiencing a renaissance of understanding about the fundamental forces of nature. The standard model was taking shape. Quantum field theory was maturing into a precise mathematical framework, and physicists were beginning to appreciate the profound role that spontaneous symmetry breaking played in determining the structure of reality. It was within this fertile ground of discovery that the seeds of vacuum metastability theory were planted. The context that gave birth to their dangerous idea was the growing recognition that the vacuum state of quantum fields, what we experience as empty space, was far more complex and interesting than anyone had previously imagined. Earlier work by other physicists had revealed that the vacuum could exist in different phases, much like water can exist as ice, liquid, or vapor. But Coleman and DeLucia pushed this analogy further, asking what would happen if the vacuum were currently in a metastable phase, stable for now, but not necessarily forever. Meanwhile, across the broader landscape of physics, quantum mechanics was revealing its most counterintuitive aspects. The phenomenon of quantum tunneling, the ability of particles to pass through barriers that classical physics deemed impenetrable, was becoming well established through laboratory experiments. Electrons could tunnel through electrical barriers, atoms could tunnel through energy barriers in chemical reactions, and the very fusion processes that power the stars depended on quantum tunneling to overcome the electromagnetic repulsion between atomic nuclei. Coleman and DeLuca's genius lay in recognizing that if individual particles could tunnel through energy barriers, then perhaps entire regions of space-time could tunnel from one vacuum state to another. This was a conceptual leap of breathtaking audacity. The idea that the fabric of reality itself might be subject to the same quantum uncertainty that governed the behavior of subatomic particles. As we drift deeper into their revolutionary thinking, we encounter the mathematical elegance that would become their legacy. Their calculations revealed that if the universe existed in a false vacuum state, it could theoretically tunnel to a more stable configuration through the formation of what they called bubbles of true vacuum. These bubbles would nucleate randomly in space, expand at the speed of light, and convert everything in their path to a new vacuum state with potentially very different physical properties. The implications of their work sent ripples through the physics community, like stones dropped into a still pond. Here was a theory that suggested our entire universe, with all its apparent permanence and stability, might be nothing more than a temporary arrangement, a cosmic configuration that could persist for eons, but remained fundamentally vulnerable to a transition that would erase everything we know and replace it with something entirely alien. Yet this is only the beginning of the story that Coleman and DeLuca unleashed upon the world. Their work represented more than just a new possibility for cosmic catastrophe. It embodied a profound shift in how physicists thought about the nature of space-time itself. No longer could space be conceived as a passive stage upon which particles played out their quantum dramas. Instead, space itself became an active participant, a dynamic medium whose properties could change, whose stability could not be taken for granted. There is something both humbling and beautiful about the way their theory emerged from pure mathematics, from following equations wherever they led, regardless of the implications for human comfort or cosmic security. This represents science at its most honest and courageous, the willingness to pursue truth, even when that truth might be unsettling, the commitment to understanding reality even when reality proves to be stranger and more precarious than we ever imagined. The revolution in thinking that Coleman and DeLuca initiated extended far beyond the specific question of vacuum stability. Their work helped establish a new paradigm in cosmology, one that recognized the universe as a dynamic, evolving system where even the most fundamental properties of space-time could be subject to change. This perspective would later prove crucial for understanding cosmic inflation, the multiverse hypothesis, and the role of quantum fluctuations in determining the large-scale structure of the universe. Perhaps the most profound aspect of their contribution was how it connected the smallest scales of quantum mechanics to the largest scales of cosmology. The same quantum uncertainty that allows an electron to tunnel through a barrier in a laboratory experiment might also allow the entire universe to tunnel from one vacuum state to another. This unification of the microscopic and the cosmic represents one of the most beautiful achievements of modern theoretical physics. And in this dance between mathematical necessity and cosmic possibility, between theoretical elegance and existential uncertainty, we find ourselves contemplating not just a scientific theory, but a meditation on the nature of existence itself. For Coleman and DeLucia had discovered that the universe might be far more creative, far more dynamic, and far more surprising than even physicists had dared to imagine. There is something almost mystical about quantum tunneling, this fundamental process that allows particles to accomplish what should be impossible, to pass through barriers as if they were ghosts moving through walls. Tonight, we explore this quantum magic trick that operates at the heart of reality, from the smallest atomic scales to potentially the entire cosmos itself, revealing how the universe performs feats that challenge our most basic intuitions about the nature of possibility and impossibility. Picture, if you will, a marble rolling toward a hill. In the classical world of our everyday experience, this marble faces a simple choice. Either it possesses enough energy to roll over the hill, or it will come to rest against the slope and remain there indefinitely. The barrier is absolute, the boundary clear, the outcome predictable. Yet in the quantum realm, where the fundamental laws of nature reveal their most surprising aspects, particles face no such limitations. Imagine that same marble, now shrunk to quantum dimensions, approaching its energy barrier. Instead of simply bouncing back or rolling over, something far more remarkable occurs. There exists a probability, however small, that the marble will simply appear on the other side of the hill, having passed through solid matter as if it were nothing more than morning mist. This is quantum tunneling, nature's gentle defiance of our classical expectations, a reminder that reality operates according to principles far more subtle and strange than our macroscopic experience might suggest. The mathematics that describe this phenomenon possess their own austere beauty, equations that transform the absolute boundaries of classical physics into fuzzy probabilities, walls into permeable membranes. The Schrödinger equation, that fundamental description of quantum behavior, reveals that particles do not exist as solid, localized objects, but as waves of probability that can extend beyond the classical boundaries that should contain them. Meanwhile, in laboratories around the world, quantum tunneling reveals itself through countless experiments and practical applications. In the heart of every star, including our own sun, nuclear fusion occurs only because protons can tunnel through the electromagnetic barriers that would otherwise prevent them from combining. Without this quantum magic, stars would never ignite, and the universe would remain dark and cold, devoid of the complex chemistry necessary for life. There is something almost musical about the way tunneling probability depends on the properties of the barrier. The thicker the barrier, the less likely the tunneling. The higher the barrier, the more improbable the passage. Yet no barrier, no matter how formidable, reduces the probability to exactly zero. Even the most massive walls retain a whisper of permeability, a ghost of possibility that particles might pass through them. As we drift deeper into this quantum mystery, we encounter the scanning, tunneling microscope, that marvel of modern technology that allows us to image individual atoms by exploiting the tunneling of electrons across tiny gaps. Here, the abstract mathematics of quantum mechanics transforms into practical capability, allowing us to see and manipulate matter at its most fundamental level, to write with individual atoms and read the quantum signatures of surfaces atom by atom. Yet this is only the beginning of tunneling's cosmic significance, for what Coleman and DeLucia realized in their revolutionary work was that entire regions of space-time might be subject to the same quantum uncertainty that governs individual particles. If a single electron can tunnel through a barrier, then perhaps a bubble of space containing trillions upon trillions of atoms could tunnel from one vacuum configuration to another. The application of quantum tunneling to cosmological scales represents one of the most audacious intellectual leaps in modern physics. Consider the energy barriers that separate different vacuum states, barriers that might be impossibly high from the perspective of classical physics, requiring more energy than exists in the observable universe to overcome through normal means. Yet quantum tunneling whispers a different possibility, that these barriers, however formidable, are not absolute boundaries, but statistical suggestions. There is something profoundly beautiful about the way tunneling connects the intimate and the infinite. The same quantum principles that allow the hemoglobin in your blood to bind oxygen molecules, that enable the chemical processes in your brain to generate consciousness, that permit plants to harvest sunlight through photosynthesis. These same principles might one day allow the entire universe to transform itself into something completely different. The probability calculations for cosmic vacuum tunneling stretch our mathematical capabilities to their limits. The numbers involved are so small that they mock our usual concepts of likelihood, so infinitesimal that the tunneling event might not occur until long after every star has died, every black hole has evaporated, and every proton in the universe has decayed. Yet the probability remains finite, a reminder that even the most stable-seeming arrangements in nature retain an element of quantum uncertainty. Perhaps the most remarkable aspect of quantum tunneling is how it reveals the creative potential hidden within apparent impossibility. What seems forbidden from one perspective becomes merely improbable from another, and what appears permanent from our limited viewpoint emerges as temporary when viewed through the lens of quantum mechanics. This transformation of absolutes into probabilities, of certainties into suggestions, represents one of quantum theory's most profound contributions to our understanding of reality. In the gentle darkness of contemplation, we can appreciate tunneling as more than just a physical phenomenon. It becomes a metaphor for the universe's endless creativity, its ability to discover new possibilities, even within apparently rigid constraints. Every moment, in every cubic centimeter of space, quantum fields explore possibilities that classical physics would deem impossible, and occasionally, very occasionally, they succeed in creating something new. And in this dance, between the possible and the impossible, between barriers and passages, between the forbidden and the merely improbable, we find ourselves participants in a cosmic experiment whose outcomes remain forever uncertain, forever surprising, forever beautiful in their quantum ambiguity. The universe tunnels through its own possibilities, and we, conscious beings made of tunneling particles, contemplate the tunneling of consciousness itself through the barriers between ignorance and understanding. In the vast symphony of quantum fields that fill every corner of space, there exists one field so fundamental, so essential to the nature of reality, that its discovery represented one of the greatest triumphs in the history of physics. Tonight, we turn our gentle attention to the Higgs field, that invisible cosmic medium that gives mass to particles and structure to the universe, yet whose stability determines whether our familiar reality can continue to exist or must yield to some vastly different arrangement of the fundamental forces. Picture, if you will, the entire universe as an ocean, not of water, but of pure potential, an infinite sea of quantum energy that extends from the smallest subatomic scales to the largest cosmic structures. This is the Higgs field, a scalar field that permeates all of space, creating the very possibility of mass, of inertia, of the resistance that particles encounter as they try to move through the vacuum of space. Without this field, electrons would be massless, atoms could not form, and the intricate architecture of matter that makes complexity possible would simply not exist. The story of the Higgs field's discovery reads like a detective novel spanning half a century. In the 1960s, physicist Peter Higgs and several of his colleagues proposed that empty space was not actually empty, but filled with an invisible field that had fallen into its lowest energy state. This field would interact with particles as they moved through it, slowing some down and giving them the property we experience as mass, while allowing others, like photons, to pass through unimpeded at the speed of light. There is something almost mystical about the way the Higgs mechanism works. Imagine particles as swimmers moving through a cosmic medium that offers different amounts of resistance depending on their type. Electrons struggle through this medium and acquire mass. Protons encounter even more resistance and become more massive still, while photons glide through effortlessly, remaining eternally massless and swift. The Higgs field acts like a cosmic molasses, but one that affects different particles in precisely the ways needed to create the stable atoms and molecules that make our world possible. For decades, this remained a beautiful theory without experimental confirmation, a mathematical framework that explained much, but whose central prediction, the existence of the Higgs boson, remained tantalizingly beyond reach. The Higgs boson itself is a ripple in the Higgs field, an excitation that could be created by colliding particles at enormous energies, like striking a cosmic bell and listening for its characteristic note. Meanwhile, across the underground chambers of the Large Hadron Collider, thousands of physicists and engineers constructed the most complex machine ever built by human beings, a device capable of accelerating protons to nearly the speed of light and colliding them with energies that hadn't existed in the universe since the first moments after the Big Bang. In July 2012, after decades of searching, they announced the discovery of a new particle consistent with the long-sought Higgs boson. The confirmation of the Higgs field's existence was more than just a victory for particle physics. It was a validation of our understanding of the quantum foundations of reality. Here was experimental proof that empty space was indeed filled with an invisible field, whose properties determine the basic characteristics of matter. Yet this triumph came with a sobering realization. If the Higgs field could exist in its current state, it might also be capable of existing in other states, potentially more stable ones. As we drift deeper into the implications of Higgs field stability, we encounter one of the most profound questions in modern cosmology. Current measurements suggest that the Higgs field might exist in what physicists call a metastable state. Stable for now, but potentially vulnerable to tunneling into a deeper energy minimum that would have catastrophic consequences for the structure of matter as we know it. The delicate dance between quantum fields that determines our universe's stability centers largely on the Higgs field's behavior. The field's current value, what physicists call its vacuum expectation value, determines not only the masses of fundamental particles, but also their interactions with each other. Change this value, and the entire periodic table would be rewritten. The forces that bind atomic nuclei would shift, and the chemistry that makes life possible would become impossible. There is something both beautiful and terrifying about the precision required for our universe to exist in its current form. The Higgs field must have exactly the right value to allow stable atoms, exactly the right interactions with other fields to permit complex chemistry, exactly the right relationship with the electromagnetic and strong nuclear forces to make stars and planets possible. Too strong, and atoms would be bound so tightly that chemical reactions couldn't occur. Too weak, and matter would fly apart before structure could emerge. Yet the calculations that attempt to determine the true stability of the Higgs field push the boundaries of our current understanding. The measurements depend on precise knowledge of other fundamental constants, particularly the mass of the top quark and the strength of the strong nuclear force, and small uncertainties in these values translate into large uncertainties about the field's ultimate fate. Perhaps the most remarkable aspect of the Higgs field's role in vacuum metastability is how it connects the everyday world of atoms and molecules to the deepest questions about cosmic destiny. The same field that gives mass to the carbon atoms in your body, that determines the weight of the water you drink and the air you breathe, also holds within its quantum fluctuations the potential for a transformation that would remake reality itself. In the gentle contemplation of this cosmic interdependence, we find ourselves marveling at the intricate web of relationships that make existence possible. The Higgs field does not work alone, but interacts with all the other quantum fields in a cosmic ballet of extraordinary precision and beauty. Each field influences every other field, creating a harmonious whole that is far more stable and resilient than any individual component. And in this dance of fields and forces, of stability and transformation, of the known and the unknowable, we discover that we are not merely observers of cosmic processes, but integral participants in them. The Higgs field that gives structure to our bodies is the same field whose stability determines the future of all matter in the universe, connecting us intimately to the deepest mysteries of existence. Through the very atoms from which we are made, there is something hauntingly beautiful about the equations that describe the end of everything, mathematical expressions so elegant they could serve as poetry, yet containing within their symbols and relationships the potential for transformations so complete they challenge our very conception of permanence. Tonight, we explore the mathematical framework that governs vacuum metastability, where numbers and symbols dance together to reveal probabilities so small they seem almost merciful, timescales so vast they dwarf our usual concepts of eternity. Picture, if you will, the equation that describes the rate at which vacuum bubbles might spontaneously nucleate in space, a formula that looks deceptively simple until you begin to unpack the profound physics it contains. The tunneling probability depends exponentially on what physicists call the action of the tunneling path, a quantity that encodes the energy barrier between our current vacuum state and any potential lower energy configurations. This exponential dependence means that even modest increases in the barrier height lead to astronomically small probabilities. The beauty of these mathematical relationships lies not just in their formal elegance, but in what they reveal about the cosmic balance between stability and change. The action integral, that central quantity in the tunneling calculation, represents a kind of mathematical resistance to change, the universe's natural conservatism expressed in the language of quantum field theory. The larger the action, the more reluctant the universe becomes to abandon its current configuration, even if a more favorable one exists. Meanwhile, across the vast landscape of probability theory, we encounter numbers so small they challenge our ability to conceive of them meaningfully. The probability of a vacuum decay in any given cubic meter of space in any given second might be something like 10 to the negative power of several hundred, a number so close to zero that it would remain effectively zero, even if multiplied by the number of cubic meters in the observable universe and the number of seconds since the Big Bang. There is something almost meditative about contemplating these infinitesimal probabilities. They remind us that the universe operates according to principles of such precision that events which are theoretically possible might still be practically impossible on any timescale we can meaningfully consider. The mathematics suggests that vacuum decay could happen, but also whispers that it might not happen for periods of time so long they make the current age of the universe seem like a brief moment. The equations that govern bubble nucleation possess their own austere poetry, describing how regions of true vacuum would grow if they ever formed. The bubble wall would expand at the speed of light, carried by the pressure difference between the two vacuum states, converting everything in its path to the new configuration with the inevitability of mathematics itself. Yet the formation of that first bubble remains governed by probabilities so small they approach the mathematical concept of zero without ever quite reaching it. As we drift deeper into these mathematical mysteries, we encounter the profound relationship between energy and time that governs all quantum tunneling phenomena. Heisenberg's uncertainty principle allows energy conservation to be temporarily violated, but only for periods inversely proportional to the energy borrowed. For vacuum tunneling on cosmic scales, the energy involved is so enormous that the tunneling time becomes correspondingly brief. Not brief in human terms, but brief compared to the astronomical timescales over which the process must occur. The temperature dependence of tunneling rates adds another layer of mathematical elegance to our story. In the early, hot universe, thermal fluctuations could have provided additional pathways for vacuum transitions, potentially making them more likely than they are in our current cold cosmos. The equations reveal how the universe's cooling over cosmic time has made it increasingly stable against vacuum decay, as if time itself conspires to preserve the current configuration of reality. Perhaps the most beautiful aspect of the mathematics lies in how it connects the quantum and the cosmic. The same Schrödinger equation that describes an electron tunneling through a barrier in a laboratory also, when properly generalized, describes the potential tunneling of spacetime itself from one vacuum configuration to another. This unification of scales, this recognition that the same mathematical principles operate from the subatomic to the cosmic, represents one of physics' greatest intellectual achievements. The role of topology in vacuum stability adds yet another dimension of mathematical beauty to our contemplation. The shape of the energy landscape in the abstract space of field configurations determines not just which transitions are possible, but also their relative probabilities. Valleys, connected by narrow mountain passes, have different tunneling characteristics than those separated by broad, high plateaus, and the mathematics captures these geometric subtleties with exquisite precision. There is something profoundly moving about the way uncertainty enters these calculations. Despite our sophisticated mathematical framework, despite our precise equations and elegant formalism, we cannot know with certainty whether we live in a stable or metastable vacuum. The calculations depend on parameters: the Higgs mass, the top quark mass, the strength of various coupling constants that we know only approximately, and small uncertainties in these fundamental quantities translate into enormous uncertainties about our ultimate fate. Yet this mathematical uncertainty serves not as a limitation, but as a reminder of the universe's essential creativity. The equations suggest multiple possibilities, a range of potential futures that remain genuinely open. We exist in a cosmos where the mathematics itself preserves mystery, where even our most sophisticated theories leave room for surprise, for outcomes that cannot be predicted with certainty, no matter how precisely we measure or how carefully we calculate. In the gentle darkness of mathematical contemplation, we can appreciate these equations not just as tools for prediction, but as expressions of the universe's deepest character. They reveal a cosmos that balances stability with change, permanence with transformation, the known with the unknowable. The same mathematical principles that threaten our existence also make it possible. The same uncertainties that create cosmic anxiety also create cosmic wonder. And in this dance of numbers and possibilities, of infinitesimal probabilities and infinite consequences, we find ourselves part of a universe far more mathematically beautiful than we ever dared imagine. A cosmos where even destruction, should it ever come, would arrive clothed in the elegant mathematics that govern all of existence. In the gentle darkness of our contemplation, we must now envision something both terrible and strangely beautiful: the birth and growth of what physicists call a true vacuum bubble, a sphere of transformed reality that would expand through space with the relentless precision of light itself, carrying within its advancing boundary the complete reformation of everything we understand as existence. There is something almost serene about this cosmic transformation, a paradoxical peace in the idea of total change propagating through the universe with mathematical inevitability. Picture, if you will, the moment of nucleation, that quantum instant when somewhere in the vast emptiness between galaxies, or perhaps in the heart of a distant star, or maybe in the space between the atoms of your own body, the quantum fields finally discover a deeper valley in the energy landscape they have been exploring for nearly 14 billion years. This moment would not announce itself with fanfare or warning. It would simply be a microscopic bubble of new reality appearing as spontaneously as virtual particles emerge from the quantum foam. The bubble itself would be smaller than an atom at first, a tiny sphere containing space, configured according to different physical laws, where the fundamental constants might have different values, where particles might behave in alien ways, where the very meaning of matter and energy could be transformed beyond recognition. Yet this insignificant seeming bubble would carry within it the seed of universal transformation, growing with the unstoppable determination of expanding space-time itself. There is something almost musical about the way such a bubble would grow. The mathematics describe an acceleration driven by the pressure difference between the false vacuum outside and the true vacuum within, a cosmic imbalance that would power the bubble's expansion at exactly the speed of light. No force in the universe could overtake this expanding boundary. No signal could warn of its approach. No escape would be possible for anything in its path. As the bubble expanded, consuming cubic light year after cubic light year of space, it would encounter the magnificent structures of our cosmos with perfect indifference. Galaxies billions of years old, their stars having burned for eons, their planets having nurtured countless seasons of change and evolution, would meet the advancing boundary and simply cease to exist as we understand existence. Not destroyed in the violent sense of explosion or collapse, but transformed, converted instantly into whatever forms of matter and energy are stable in the true vacuum state. Meanwhile, from our perspective, within the false vacuum, this transformation would remain forever invisible until the moment it reached us. The bubble wall travels at light speed, which means no information about its approach could possibly arrive before the transformation itself. The universe would appear completely normal until the very instant that reality itself was redefined around us. There is something profoundly moving about the elegance of this process. The same speed of light limit that prevents us from seeing our cosmic destruction approaching also represents one of the fundamental symmetries of space-time, the invariant speed that connects space and time, that governs the propagation of all forces and information. Even in transformation, the universe would respect its own most basic geometric principles. The boundary between false vacuum and true vacuum would be extraordinarily thin, perhaps no thicker than the wavelength of an elementary particle. Yet across this razor-sharp divide, two completely different universes would meet. On one side, our familiar reality with its atoms and molecules, its electromagnetic forces and nuclear interactions, its delicate balances that allow for complexity and consciousness. On the other side, something potentially unrecognizable, a realm where the basic rules of physics might be so different that nothing resembling our current understanding of matter could exist. As we drift deeper into this visualization, we encounter the beautiful paradox of peaceful destruction. Unlike the violent ends we typically imagine for cosmic catastrophes, the crushing collapse of gravitational waves, the searing heat of stellar explosions, the grinding chaos of galactic collisions, vacuum decay would arrive with quiet efficiency. There would be no suffering, no struggle, no gradual decline. The transformation would be instantaneous and complete, more like a gentle editing of reality's fundamental code than a destructive force in any conventional sense. Yet this is only the beginning of our contemplation of the bubble's cosmic journey, for should such a nucleation event ever occur, the expanding bubble would not remain alone. The same quantum fluctuations that created the first bubble could create others, and these secondary bubbles would expand until they met the boundaries of the first, creating an ever more complex pattern of overlapping spheres of true vacuum. The universe would become a cosmic foam of transformation, with different regions potentially settling into different stable configurations. The temperature at the boundary between vacuum states would be beyond anything in our current experience, energies comparable to those that existed in the first moments after the Big Bang would be released, as the vacuum energy difference converted itself into the kinetic energy of expanding spacetime. Yet this tremendous heat would exist only at the boundary itself, a moving interface between two different versions of reality. Perhaps the most beautiful aspect of contemplating this cosmic bubble is how it connects us to the fundamental creativity of the universe. The same quantum uncertainty that makes vacuum decay possible also makes consciousness possible. The same field fluctuations that could someday transform our reality are the fluctuations that allowed galaxies to form from the smooth early universe, that permitted the complexity necessary for stars and planets, and ultimately for beings capable of contemplating their own cosmic context. There is something almost mystical about the way the bubble would carry within it a new definition of possibility itself, not just new physical laws, but new relationships between space and time, new forms that matter and energy could take, new types of structure that might emerge in a universe governed by different fundamental principles. The bubble of annihilation is simultaneously a bubble of creation, an expanding sphere of cosmic reinvention that would write new chapters in the story of existence. In the quiet contemplation of this ultimate transformation, we find ourselves face to face with the universe's most profound teaching about impermanence and change. Even the most fundamental aspects of reality, the laws of physics themselves, might be temporary features of a cosmos far more creative and dynamic than we ever dared imagine. And in this recognition, we discover not terror, but wonder at being part of a universe capable of such extraordinary transformations, such cosmic creativity, such beautiful and complete renewal. In the vast tapestry of cosmic time, where billions of years pass, like seasons, and the birth and death of stars mark the slow rhythm of universal change, we encounter numbers so large they challenge our ability to conceive of duration itself. Tonight, we drift through these unimaginable timescales, where the probability of vacuum decay plays out against a temporal backdrop so extended that it transforms our understanding of what it means for something to be permanent or temporary, likely or unlikely, threatening or benign. Picture, if you will, a single second of your life, perhaps this moment, as you listen to these words, as your heart beats once, as a single thought moves through your consciousness. Now imagine stretching that second into a year, that year into a century, that century into the entire history of human civilization. Continue this expansion through the age of our planet, through the lifetime of our sun, through the current age of the universe itself, and you will have barely begun to approach the timescales on which vacuum metastability operates. The calculations that physicists use to estimate vacuum decay probabilities yield numbers that exist in a realm beyond ordinary comprehension. Consider a probability so small that the expected time between vacuum decay events might be 10 to the power of 500 years, a number that dwarfs not only the current age of our universe, which is a mere 13.8 billion years old, but also the projected lifetimes of the longest lived stars, the slowest stellar evolution, and even the speculative timescales on which protons themselves might decay. There is something almost meditative about contemplating these vast temporal expanses. They remind us that our universe, despite feeling ancient and permanent from our brief human perspective, is actually quite young in terms of the fundamental timescales that govern quantum field behaviors. We exist in what might be called the early universe, not the first moments after the Big Bang, but the first tiny fraction of the time during which our current vacuum configuration might be expected to persist. Meanwhile, in the life cycles of stars, we find more familiar benchmarks for cosmic time. Our sun will continue burning hydrogen for another 5 billion years, gradually brightening until Earth becomes uninhabitable. It will then expand into a red giant, cool into a white dwarf, and slowly fade over trillions of years until it becomes a cold, dark ember. Yet even this enormous span, from our sun's birth to its final extinction, represents only the briefest flicker compared to the timescales on which vacuum decay operates. The mathematics reveal a beautiful relationship between probability and time that governs all quantum processes. Events that are extraordinarily unlikely in any given moment become increasingly probable when given enormous amounts of time to occur. Yet for vacuum decay, the probabilities are so infinitesimally small that even granting them time periods that exceed the age of the universe by factors of hundreds of orders of magnitude still leaves the expected occurrence comfortably in the realm of effectively never. As we drift deeper into these temporal contemplations, we encounter the profound relativity of cosmic fears. From our perspective, as beings who measure our lives in decades, even the threat of our sun's eventual death feels remote and abstract. How much more remote, then, is a process that might not occur for time periods that make stellar evolution seem instantaneous? The numbers suggest that we could witness trillions of generations of stars, the formation and dissolution of countless galaxies, and the complete thermal death of the universe as we know it, all while our vacuum state remains perfectly stable. Yet this is only the beginning of our journey through deep time, for beyond the stars lies an even more extended future, where the universe continues to expand and cool, where matter itself begins to decay, where black holes slowly evaporate through Hawking radiation, and where even space becomes a dark, empty stage populated only by the occasional flash of virtual particles appearing and vanishing in the quantum foam. Even in this far future, vacuum decay would still be unlikely to have occurred. The comparison between vacuum decay timescales and other cosmic processes reveals the extraordinary stability of our current configuration. Consider that the proton, one of the most stable particles we know, might have a half-life of 10 to the 34th power years, an unimaginably long time that nonetheless appears brief compared to vacuum decay estimates. This suggests that even if all the protons in the universe decay, even if matter as we know it completely disappears, our vacuum state might still persist unchanged. There is something profoundly comforting about these calculations, not because they guarantee our safety, for the probabilities, however small, remain finite, but because they reveal the extraordinary robustness of the quantum mechanical foundations upon which our reality rests. The same mathematical framework that allows for vacuum decay also demonstrates how unlikely such an event truly is, how well protected we are by the sheer improbability of the transition. Perhaps the most beautiful aspect of contemplating these vast timescales is how they reframe our understanding of cosmic anxiety. Fears that might seem reasonable when contemplating processes that could occur within millions or even billions of years become almost absurd when the relevant timescales stretch beyond 10 to the 100th power years. The universe grants us not just safety, but safety by margins so vast they border on the infinite. In the gentle darkness of temporal contemplation, we can appreciate how these numbers connect us to the deepest principles of quantum mechanics. The same uncertainty that makes vacuum decay theoretically possible also ensures that it remains practically impossible for durations that exceed our wildest concepts of permanence. We exist in a universe that is simultaneously vulnerable to transformation and protected from it by timescales so extended they approach eternity. The mathematics of deep time also reveal something profound about the nature of possibility itself. Events that are theoretically possible but probabilistically negligible occupy a special category in our understanding of reality. They remind us that the universe contains infinite potential while remaining practically stable and predictable. This balance between theoretical possibility and practical impossibility represents one of quantum mechanics' most elegant gifts to cosmic philosophy. And in this dance between the possible and the probable, between the theoretical and the practical, between the instantaneous and the eternal, we find ourselves inhabitants of a universe that manages to be simultaneously dynamic and stable, creative and conservative, uncertain and reliable. The same quantum fields that could theoretically destroy us also protect us through probabilities so small they transform cosmic catastrophe into cosmic comedy, universal destruction into universal patience, existential terror into existential peace. In the quiet chambers of quantum possibility, we encounter one of physics' most profound distinctions: the difference between states that appear stable and those that are truly stable, between temporary equilibrium and permanent rest, between the false vacuum in which we might live and the true vacuum toward which the universe might someday evolve. Tonight, we explore this cosmic dichotomy through the gentle lens of familiar analogies, discovering how the universe might exist in a state of apparent permanence that conceals deeper possibilities for transformation. Picture, if you will, a marble resting peacefully in a shallow bowl, motionless and seemingly secure. To all appearances, this marble has found its natural place, a position of stability where it could remain indefinitely. Yet imagine that this bowl sits atop a table, and beneath the table lies a deep cave, and at the bottom of that cave stretches an even deeper valley. The marble in its shallow bowl knows nothing of these hidden depths, feels no pull toward the greater stability that lies far below. Yet its current position, comfortable though it may be, represents only a temporary arrangement, a way station rather than a final destination. This homely metaphor captures something essential about the distinction between false and true vacuum states. Our universe, with all its apparent permanence and reliability, might be like that marble in its shallow bowl, stable enough for our purposes, persistent enough to allow for the evolution of galaxies and stars and life, yet vulnerable to a transition that would carry it to a much deeper, more fundamental state of equilibrium in our current false vacuum, if that is indeed what it is. The laws of physics have arranged themselves in patterns that permit extraordinary complexity. Atoms can form stable bonds, creating the molecular architectures necessary for chemistry and biology. Electrons orbit nuclei in predictable patterns. Electromagnetic forces balance nuclear forces in precise ratios, and the fundamental constants maintain values that allow for the delicate dance between matter and energy that makes our familiar world possible. There is something almost miraculous about the precision required for this complex equilibrium. The strength of the electromagnetic force must be exactly right to allow atoms to bind without crushing their nuclei. The mass ratios between different particles must fall within narrow ranges to permit stable chemistry, and the energy density of the vacuum itself must be small enough to allow space to expand gradually rather than explosively. Our false vacuum, if that is what we inhabit, represents a cosmic sweet spot of extraordinary improbability. Meanwhile, in the hypothetical true vacuum toward which we might someday evolve, everything could be different. The fundamental constants that govern particle physics might take on new values, creating a universe where electrons are more massive or less massive, where photons interact differently with matter, where the forces between particles follow entirely different rules. The periodic table might be rewritten. Stellar evolution might proceed along unfamiliar pathways, and the types of complexity that could emerge might be utterly alien to our current experience. As we drift deeper into this comparison, we encounter the beautiful paradox of metastability in everyday experience. Consider water held just above its freezing point, liquid, but ready to crystallize into ice at the slightest disturbance. Or think of a solution supersaturated with dissolved sugar, clear and stable until a single crystal provides a nucleation site around which the excess solute suddenly precipitates. These familiar phenomena mirror, on a microscopic scale, the relationship between our potentially false vacuum and the true vacuum that might lie hidden beneath. Yet this is only the beginning of our exploration of vacuum states, for the transition from false to true vacuum would not be a gentle evolution like water slowly cooling into ice, but an instantaneous transformation that would redefine the very meaning of matter and energy. Imagine if the molecular structure of water could suddenly discover a more stable arrangement, not a different crystal form, but an entirely different type of substance, with completely different properties and behaviors. The true vacuum, should it exist, would represent what physicists call the ground state of all quantum fields, their lowest possible energy configuration, their most comfortable and permanent arrangement. In such a state, the universe would achieve a kind of cosmic contentment, with no further possibility of decay to even lower energy states. Everything would be perfectly stable, though that stability might come at the cost of the complex interactions that currently make life and consciousness possible. There is something both terrifying and beautiful about contemplating the differences between these vacuum states. Our false vacuum, with all its apparent complexity and richness, might be nothing more than an elaborate temporary arrangement, like a sandcastle built at low tide, beautiful and intricate, but destined eventually to be swept away by forces beyond its control. Yet this temporary nature doesn't diminish its reality or importance. It simply places it in the broader context of cosmic possibility. The energy difference between false and true vacuum states would be released in any transition between them, potentially providing the driving force for the bubble expansion we explored earlier. This energy, stored invisibly in the very fabric of space itself, represents a cosmic battery that has been charging for nearly 14 billion years, accumulating potential that could power transformations beyond our current imagination. Perhaps the most profound aspect of the false versus true vacuum distinction is what it reveals about the nature of physical law itself. What we experience as immutable constants and inviolable principles might actually be temporary features of a particular vacuum configuration. The speed of light, the charge of the electron, the strength of gravity. All of these could potentially change in a transition to true vacuum, revealing that even the most fundamental aspects of reality might be contingent rather than absolute. In a universe of true vacuum, new forms of complexity might emerge that we cannot currently imagine. Different particle masses might allow for different types of atomic nuclei. Altered force strengths might permit new forms of chemical bonding, and completely novel physical processes might become possible. The true vacuum might support its own forms of structure and organization, its own equivalent of stars and planets, perhaps even its own pathways to consciousness and intelligence. There is something deeply humbling about recognizing that our entire universe, with all its beauty and complexity, might represent just one chapter in a much larger story of cosmic possibility. The false vacuum that nurtures us might be like a cocoon that has served its purpose, ready to transform into something utterly different, yet potentially even more magnificent. And in this dance between the temporary and the permanent, between the false and the true, between what is and what might be, we find ourselves contemplating not just the nature of vacuum states, but the nature of existence itself, discovering that even the most fundamental aspects of reality might be works in progress, temporary arrangements in an ongoing cosmic exploration of possibility and becoming. In the vast orchestra of cosmic forces that shape the universe's destiny, there plays a mysterious melody that astronomers call dark energy, a pervasive influence that drives the accelerating expansion of space itself, stretching the fabric of reality and carrying galaxies away from each other with increasing speed. Tonight, we explore the profound connections between this cosmic acceleration and the question of vacuum stability, discovering how the energy hidden in empty space itself might hold the key to both our universe's current behavior and its ultimate fate. Picture, if you will, the universe as a cosmic balloon expanding steadily since the Big Bang, carrying galaxies on its surface like dots marked on rubber that stretches in all directions. For billions of years, astronomers expected this expansion to slow down, gradually overcome by the gravitational attraction of all the matter the universe contains. Yet in the 1990s, careful observations of distant supernovas revealed something shocking. The expansion is not slowing down, but speeding up, as if some invisible force is pushing space itself apart with increasing vigor. This acceleration requires an energy source, and the most natural candidate is the quantum vacuum itself, the same empty space whose stability we have been contemplating throughout our journey. The energy density of the vacuum, though potentially tiny, is spread throughout every cubic centimeter of space, and when multiplied by the enormous volume of the observable universe, it could provide exactly the kind of steady, persistent force needed to drive cosmic acceleration. There is something almost poetic about the way vacuum energy connects the smallest and largest scales in physics. The same quantum fluctuations that create virtual particles in laboratory experiments might also be responsible for the grandest phenomenon in cosmology, the accelerating expansion that will ultimately determine whether galaxies continue to move apart forever or eventually reverse course and collapse back together. The intimate becomes cosmic, the microscopic becomes universal in a way that exemplifies the deep unity underlying all physical phenomena. Meanwhile, the mathematical framework that describes dark energy introduces what physicists call the cosmological constant, a term that Einstein first added to his equations of general relativity, then rejected, then saw resurrect itself decades later as the best explanation for cosmic acceleration. This constant represents the energy density of empty space, a fixed amount of energy per unit volume that remains constant even as space expands, creating more volume and thus more total energy as the universe grows. The relationship between the cosmological constant and vacuum, metastability, opens up possibilities, both beautiful and unsettling. If our universe exists in a false vacuum state, then a transition to true vacuum would not only change the fundamental properties of matter, but also alter the cosmological constant itself. The energy density of empty space could suddenly jump to a different value, potentially transforming the universe's expansion in ways that would make our current cosmic acceleration seem gentle by comparison. As we drift deeper into these connections, we encounter one of the most profound puzzles in modern physics: the problem of vacuum energy calculation. When physicists try to calculate the energy density of the quantum vacuum using their best theories, they arrive at numbers that are larger than the observed value of the cosmological constant by factors of 10 to the 120th power, a discrepancy so enormous it represents one of the worst predictions in the history of science. This spectacular failure of calculation suggests that we are missing something fundamental about the nature of vacuum energy, about how quantum field fluctuations contribute to the geometry of space-time, about the relationship between the microscopic physics of particles and fields and the macroscopic behavior of the cosmos as a whole. The connection between vacuum, metastability, and dark energy might provide clues to resolving this deep mystery. Yet this is only the beginning of our exploration of cosmic implications, for the current value of the cosmological constant appears to be remarkably fine-tuned for the existence of complex structure in the universe. Too small, and space would not expand fast enough to prevent gravitational collapse. Too large, and expansion would be so rapid that galaxies, stars, and planets could never form. We exist in a cosmic sweet spot that allows for both the stability needed for structure formation and the expansion needed to prevent universal collapse. The possibility that our vacuum state is metastable adds another layer of cosmic contingency to this fine-tuning. Not only must the cosmological constant have exactly the right value for our current universe, but this value must also be stable enough to persist for the billions of years needed for galaxies to form, stars to ignite, planets to cool, and life to emerge and evolve. Vacuum metastability suggests that even this apparent stability might be temporary, subject to quantum transitions that could completely alter the cosmic expansion. There is something profoundly moving about the way dark energy connects us to the ultimate fate of the universe. Current observations suggest that cosmic acceleration will continue indefinitely, carrying galaxies beyond our observational horizon, eventually leaving our local group of galaxies isolated in an expanding bubble of space. Stars will form and die, black holes will evaporate, and the universe will cool toward a state of maximum entropy and minimum activity. Yet vacuum metastability introduces uncertainty even into this far future scenario. A transition to true vacuum could completely rewrite the cosmic story, potentially leading to outcomes we cannot currently imagine. The universe might collapse instead of expanding. New types of matter might emerge that behave according to different physical laws, or entirely novel forms of cosmic evolution might become possible. Perhaps the most beautiful aspect of the connection between vacuum, metastability, and dark energy is how it reveals the universe as a dynamic, creative system where even the most fundamental properties remain subject to change and evolution. The same empty space that drives cosmic acceleration today might someday undergo a phase transition that transforms not just the expansion of space, but the very meaning of space and time themselves. In the gentle contemplation of these cosmic connections, we find ourselves participants in a universe far stranger and more creative than we ever imagined. A cosmos where the energy of empty space shapes the destiny of galaxies, where quantum fluctuations influence the geometry of spacetime, where the stability of nothingness determines the future of everything. We are temporary patterns in a cosmic dance that connects the quantum and the cosmological, the stable and the metastable, the known and the forever unknowable. And in this dance of expansion and possibility, of acceleration and transformation, of dark energy and vacuum metastability, we discover that even the largest scales of cosmic evolution remain intimately connected to the smallest scales of quantum uncertainty, reminding us that we live in a universe where mystery and wonder operate at every level of reality, from the subatomic to the cosmic, from the brief to the eternal. There is something profoundly human about our relationship with cosmic uncertainty. The way our minds evolved to navigate the immediate dangers and opportunities of daily life, struggle to process threats so vast and improbable they exist more in the realm of mathematics than experience. Tonight, we explore how we might learn to live peacefully with the knowledge that our universe rests upon foundations that, while extraordinarily stable, remain fundamentally uncertain, forever beyond our ability to guarantee or control. Picture, if you will, the delicate psychology of cosmic anxiety. We are beings who worry about tomorrow's weather, next month's bills, and next year's plans, suddenly confronted with the possibility that the very fabric of reality might someday undergo a transformation so complete that all our familiar categories of existence would become meaningless. How does consciousness, with its evolved capacity for concern and planning, process a threat that operates on timescales that dwarf not only human history, but the history of stars themselves? The philosophical tradition offers us several approaches to this cosmic uncertainty, each with its own wisdom and limitations. The Stoics would counsel us to focus on what lies within our control, our responses, our attitudes, our choices in the present moment, while accepting with equanimity those vast forces that remain forever beyond human influence. There is something deeply comforting in this ancient wisdom, this recognition that peace comes not from controlling outcomes, but from aligning ourselves with the natural flow of events, however unpredictable they might be. Meanwhile, the contemplative traditions of the East offer their own perspective on impermanence and uncertainty. Buddhism teaches that all phenomena are transient, that attachment to permanence is the source of suffering, and that wisdom lies in embracing the flowing nature of reality. From this viewpoint, the potential metastability of our vacuum state becomes not a source of terror, but a reminder of the universal truth that nothing, not even the laws of physics themselves, remains unchanged forever. The scientific approach to extreme uncertainty operates according to its own elegant principles. Science does not promise certainty, but offers instead the tools for quantifying uncertainty, for distinguishing between different types of unknowing, for making peace with probability, rather than demanding absolute answers. When faced with vacuum decay scenarios, physicists calculate not certainties, but likelihood ranges, not definitive predictions, but statistical assessments that help us understand the relative magnitude of different cosmic risks. There is something almost meditative about the way science transforms existential terror into mathematical curiosity. The same equations that reveal our potential cosmic vulnerability also demonstrate its extreme improbability, converting an abstract philosophical fear into concrete numbers that can be compared, analyzed, and placed in proper perspective. Science teaches us to fear appropriately, to reserve our anxiety for likely events while treating improbable ones with the intellectual respect they deserve, rather than the emotional weight they don't. As we drift deeper into the psychology of cosmic uncertainty, we encounter the beautiful paradox of informed ignorance. The more we learn about vacuum metastability, the more precisely we can define the boundaries of our ignorance. We know that we don't know whether our vacuum is stable or metastable, but we also know approximately how much we don't know, and we can quantify the probability ranges within which our ignorance operates. This represents a profound form of wisdom, the ability to map the territory of the unknown with scientific precision. The wisdom traditions remind us that uncertainty is not the enemy of meaning, but its essential companion, a universe where every outcome was predetermined, where no genuine novelty was possible, where the future held no surprises, would be a universe drained of wonder and possibility. The quantum uncertainty that makes vacuum decay theoretically possible is the same uncertainty that makes creativity possible, that allows for genuine choice and authentic surprise, that ensures that the future remains genuinely open rather than mechanically determined. Yet this is only the beginning of our exploration of cosmic acceptance. For perhaps the deepest wisdom about living with uncertainty comes from recognizing that we have always lived with it, have always been participants in processes far larger and more complex than we could fully understand or control. The apparent stability and predictability of our daily existence is itself a temporary arrangement, a brief moment of apparent order emerging from the vast creative chaos of cosmic evolution. The practice of living with cosmic uncertainty might begin with something as simple as stepping outside on a clear night and looking up at the stars. These points of light, seemingly permanent fixtures in our sky, are actually dynamic, evolving systems that will someday exhaust their fuel and die. The very atoms in our bodies were forged in the hearts of such stars that lived and died billions of years ago. We are temporary arrangements of stellar ash, contemplating our place in a universe that is itself a temporary arrangement of quantum fields, exploring the landscape of possibility. There is something profoundly liberating about accepting our cosmic insignificance, not as a source of despair, but as a reminder of our participation in something vastly larger and more magnificent than any individual existence. The potential metastability of our vacuum state connects us to the deepest creative processes of the universe, to the ongoing exploration of possibility that has given rise to galaxies and stars and planets and life and consciousness itself. Perhaps the most beautiful aspect of learning to live with cosmic uncertainty is how it transforms our relationship with the present moment. When we truly accept that everything we know and love exists within a framework that is itself temporary and uncertain, each sunset becomes more precious, each human connection more meaningful, each moment of wonder and beauty more worthy of our full attention and gratitude. In the gentle darkness of cosmic contemplation, we can find peace not by denying uncertainty, but by embracing it as the natural condition of existence in a creative universe. We are quantum beings living in a quantum cosmos, temporary patterns in the endless dance of possibility and actualization that has been unfolding for nearly 14 billion years and will continue long after our particular arrangement of atoms has returned to the cosmic processes from which we emerged. And in this dance of certainty and uncertainty, of knowledge and mystery, of the temporary and the eternal, we find not reasons for despair, but invitations to wonder, opportunities to participate consciously and gratefully in the universe's ongoing exploration of what it means to exist, to be aware, to contemplate the very foundations of reality from our unique perspective as conscious arrangements of quantum fields contemplating themselves. In the vast library of cosmic catastrophes, vacuum metastability represents just one volume among many fascinating treatises on universal endings, each with its own timeline, its own mechanisms, and its own strange poetry of destruction and transformation. Tonight, we place our exploration of false vacuum decay within the broader context of cosmic eschatology, discovering how the universe has provided itself with multiple pathways toward endings both gentle and violent, gradual and sudden, familiar and utterly alien. Picture, if you will, the heat death of the universe, perhaps the most serene of all cosmic endings, a scenario where the universe simply runs out of available energy like a vast machine gradually winding down. In this far future, estimated to occur over timescales of 10 to the 100th power years, stars exhaust their nuclear fuel and fade to darkness. Black holes slowly evaporate through Hawking radiation, and the universe settles into a state of maximum entropy where nothing interesting can ever happen again. It is an ending through exhaustion rather than catastrophe, death by entropy rather than violence. There is something almost Buddhist about the heat-death scenario, a cosmic nirvana where all processes cease, all temperatures equalize, and the universe achieves perfect equilibrium at just above absolute zero. No more stellar births, no more planetary formation, no more evolution of complexity, just vast, dark space, populated by the occasional flash of a virtual particle pair emerging from and returning to the quantum vacuum. Compared to this gentle fade to black, vacuum decay seems almost energetic, a cosmic transformation rather than a cosmic retirement. Meanwhile, at the opposite extreme of violence, we encounter the Big Rip, a scenario where dark energy, the mysterious force currently accelerating cosmic expansion, grows stronger over time rather than remaining constant. In this ending, the acceleration becomes so extreme that it eventually overcomes all other forces in the universe. First, galaxies are torn apart from each other, then solar systems are disrupted, then planets are separated from their stars, and finally, in the ultimate moments before the rip, even atomic nuclei are pulled apart by the expanding space between their constituent particles. Big Rip represents destruction through excess rather than exhaustion, death by acceleration rather than entropy. Where heat death whispers the universe to sleep, the Big Rip tears reality apart with exponentially increasing violence. Yet both scenarios share a certain inevitability, a sense that once the process begins, no force in the universe can stop or reverse it. They are cosmic deaths written into the fundamental equations that govern space-time itself. As we drift deeper into this catalog of endings, we encounter the Big Crunch, a scenario where the current expansion of the universe eventually reverses, drawing all matter and energy back together in a process that mirrors the Big Bang in reverse. Galaxies collide and merge, stars are torn from their orbits and consumed by increasingly massive black holes. Temperatures rise as space contracts, and eventually all matter is compressed back into the primordial singularity from which the universe first emerged. The Big Crunch holds its own poetic appeal, an ending that is also a return, a cosmic cycle that suggests the possibility of renewal and rebirth. Unlike the finality of heat death or the violence of the Big Rip, the Big Crunch implies that endings might be beginnings in disguise, that the universe might be capable of phoenix-like resurrection from its own ashes. Current observations suggest this scenario is unlikely given the apparent acceleration of cosmic expansion, but it remains mathematically possible if dark energy behaves differently than we currently understand. There is something almost musical about comparing these different cosmic endings, each with its own tempo, its own dynamics, its own aesthetic character. Heat death plays in a minor key, slow and mournful, fading gradually to silence. The Big Rip crescendos to a violent finale that ends abruptly in cosmic forte. The Big Crunch builds to a climax that resolves into a new beginning, perhaps part of an eternal cosmic symphony of expansion and contraction. Vacuum decay, our primary focus throughout this contemplation, occupies its own unique position in this cosmic taxonomy. Unlike the gradual processes of heat death or Big Rip, which unfold over cosmic epochs, vacuum decay would be instantaneous once triggered, a cosmic phase transition as sudden and complete as water freezing or a supersaturated solution crystallizing. Unlike the Big Crunch, which returns the universe to familiar conditions of extreme temperature and density, vacuum decay would transform it into something potentially unrecognizable, governed by different physical laws and inhabited by different types of matter and energy. Yet this is only the beginning of our survey of universal endings. Modern cosmology has revealed additional possibilities that blur the boundaries between ending and transformation. False vacuum decay, if it occurred, might not represent the death of the universe so much as its metamorphosis into something entirely different, a cosmic caterpillar becoming a cosmic butterfly, unrecognizable to its former self, but perhaps equally capable of beauty and complexity. Perhaps the most profound aspect of comparing these different endings is what they reveal about the creative nature of cosmic destruction. Each scenario, however catastrophic it might appear from our current perspective, represents the universe exploring new possibilities, discovering new ways of organizing matter and energy, investigating new forms of existence. Even in ending, the cosmos remains creative. The timescales associated with these different endings vary by enormous factors, creating a hierarchy of cosmic concerns. Vacuum decay and the Big Rip could theoretically occur relatively quickly. The Big Rip in perhaps 20 billion years if dark energy accelerates. Vacuum decay potentially at any moment, but probably never. The Big Crunch would require a reversal of current cosmic acceleration that seems unlikely, but remains possible. Heat death stretches so far into the future that it makes all other endings seem immediate by comparison. There is something profoundly comforting about the diversity of cosmic endings, the way the universe has provided itself with multiple possible futures rather than a single inevitable fate. This diversity suggests that even cosmic death is creative, that even universal endings are explorations rather than mere terminations. The universe appears to be conducting a vast experiment with finitude, investigating different ways of bringing stories to conclusions, while leaving open the possibility that some endings might also be beginnings. In the gentle contemplation of cosmic endings, we find not reasons for despair, but invitations to appreciate the temporary nature of everything we cherish, whether through heat, death, Big Rip, Big Crunch, vacuum decay, or some scenario yet unimagined. The universe will someday explore forms of existence very different from those we currently experience. This knowledge doesn't diminish the value of our current existence, but enhances it, reminding us that we are participants in a cosmic story of finite duration and therefore infinite preciousness. And in this dance of beginnings and endings, of creation and destruction, of the familiar and the alien, we discover that even cosmic catastrophes are expressions of the universe's endless creativity, its willingness to transform itself in service of exploring every possible form of beauty and complexity and meaning. We are temporary patterns in this eternal exploration, conscious witnesses to a universe that remains endlessly curious about its own possibilities, even unto the very ending of everything we recognize as real.